Recording in progress.
Okay.
Okay.
I will go.
All right.
I will go. Okay.
Okay.
Okay, thank you.
All right. All right.
40 minutes is fine, right?
Okay. What?
40 minutes is fine.
Ah,
For any conference.
yes.
They are not expecting.
No,
Why you saying the stories to 1 hour?
because this is for professors to come get a job.
Oh, for interviews.
Yes.
Oh, okay.
If not, it's a half an hour is fine.
Oh, okay.
Okay.
Thanks so much, President.
Okay. ¿Qué tal, Fermín? ¿Todo tranquilo?
Hola, doctor. Muy bien, todo bien, gracias por acá.
Pues a ver, aquí está un poco bajo el sonido. Déjame ver cómo lo subo. Ah, ¿cómo lo subo aquí? Aquí está el problema. Eso es. Ahora va a ser muy alto. Bueno, hay dos cosas para hoy. Aquí tengo nada más fallas. Lo primero es discutir los resultados. No sé si ya te los envió fallas.
No, doctor, es que también no había visto que me pidió la geometría completa, apenas se la envié.
Sí, pero ya tenía el resultado de
De la mitad, ¿no? Sí.
No la envió. A ver, déjame.
Bueno, no la he revisto, no creo que no me la he enviado.
No, déjame traer a Fallas. Fallas salió en un minuto, ahorita lo voy a traer de
Sí, no se preocupe.
lo voy a traer de una oreja. Fallas. No, you need to project Fallas with the results.
This is not working, so I will open your email. Sorry.
No, you could join the Zoom. Join the Zoom. And then join the Zoom and project the results that you got for there.
That's reading, see people, and Zoom, and then Zoom. Open.
You're not haven't joined. You're not here. There you are.
Yeah.
Uh-huh.
Recording progress.
Okay.
So the email.
But the email was incomplete.
I cannot open the console.
Those two figures.
Yeah, but I know the excitation, so we can expect the voltages are symmetric because we know the equations.
Yeah, but we need to see if it is applied correctly.
Yeah, but I cannot open the console here.
Okay, show whatever you have.
So I need to share, right?
Yes.
Is it shared?
It's coming. Okay, so this is what we got, Fermin, from the make it bigger, please. So this show the model first.
Yeah, the model which he sent.
So this is your model, Fermin, and
Yes, it's the half of the
half of it.
geometry.
Yes, we Then we simulated it in Fayas's computer as it was, and we got the figure on top.
Yeah.
Now go to the figure on
Yes.
top.
And
Remove,
it-
the
We removed the
excitation part in the very
the
first-
ramping of the
the
excitation.
ramping, yeah.
So we
Yeah, I
put
can
it.
see.
We
I
put
can
it.
see
full-
the inrush.
Yeah, we put it full voltage.
Mm-hmm.
3 phases, just and we just connected them. Puff.
and change the.
Yeah.
And this is what we obtained.
Yeah.
Now,
Mm-hmm.
yeah.
So I tried some experiments.
Can you hear Fayaz?
Yes. Oh, like, yeah, I can hear him.
So I tried like without doing anything. So we didn't got these results. So when professor suggested me to remove this tapering, the other terms in the voltage excitation, we got this curve, right? For the
Mhm.
but I tried well, I tried different things, just experimenting. So
Okay.
the point is that when I just used your mirror option, and then I got something like that.
Okay.
And similarly, then I tried the multiplication factors, because since this was half of the geometry, so I thought that normally when people are doing the things with half geometry or quarter geometry, they have to play with this coil length multiplication factors and coil area.
Mhm.
So I tried just for my like I just tried. So I got different things. So it's like this way. And then I tried the perfect magnet conductor boundary condition. And because I have seen this approach in one of the tutorial, but uh, I don't know why, but we I got currents. So
Too
It's-
small current.
It's
Yeah.
more current. Yeah. Do you mention that it's perfect conductor boundary, right? Perfect
Yeah.
magnetic conductor boundary. Yeah, that boundary I don't think is correct for this kind of symmetry. We use that that kind of boundary when we could the coils at half. I mean, is in the plane, which plane you have here. Can you move up please a little bit?
Yeah.
Yeah, if you could in one plane, in horizontal plane, then we use that the kind of boundary, perfect conductor magnetic boundary, because the magnetic lines are crossing perpendicular to that boundary. In this case, are when this is the boundary that we are using for this geometry is the insulating magnetic boundary, where the magnetic lines are tangential to this surface,
Yeah.
as it should be for this kind of geometry. And then, yeah, maybe that is the reason why you are getting this kind of
Yeah.
response.
So you are saying that if it is like the horizontal case, like in some
Yeah.
in the 1/4 of the geometry.
Yeah, perfect magnetic conductor. Yeah, is when you are considering that the lines are crossing the boundary, but in perpendicular direction to the surface of
Yeah, but
the
I have
symmetry
a doubt here that
surface.
in 3D we normally assume that the vector or magnetic field has all the components like X, Y, Z, and
Mhm.
yes, this horizontal component is dominant as compared to the others. Then
The yeah,
then
well,
it is limited to only horizontal thing and not this way.
yeah, no, I think it's this kind of a boundary is not for this this
But
condition.
now, I don't understand this discussion on boundaries. Why is it that
Yeah,
why is it
uh,
the file that they sent you think is not right?
No, I was just curious. I just
Uh-huh.
thought that since
But
I am trying this
but
with a full geometry.
but shouldn't you
Mhm.
be curious with reason, not just to try things?
Sorry.
Yeah, I mean the geometry they gave you, you see, it gave you the good results.
Yeah, but it's a half.
And so what's the
That's
problem?
It's a
So
half. So
the other half should be identical. So
should be identical, but
you can simulate 1/2, no problem.
Yes.
So why is it that a problem?
The problem is that because when they are doing the things with the half geometry, so they define the input as well as output for a
Yes,
coil, right? For
yes.
half coil. But when we are doing this thing, then to get the correct results, we have to use the boundary condition as well as the multiplying factor
Mhm.
to mimic that we have the complete thing.
Yeah.
So this is
But
why I'm
the model,
concerned
you
about it.
got the model already with those settings, right?
Yeah.
You only run it and it
Yeah.
gave you the good answer.
Yeah, so I mentioned earlier that I was just trying to see.
I see.
It's not like
So I see.
for my fun.
So,
Yeah, it's a,
okay, if it is for your fun, don't show it to everybody. It's only for your fun.
No, but these are the questions behind that
Okay.
with a full geometry, why
I
the
see.
behavior is not the
Okay.
same as it should be.
Okay.
Yeah, so it's so that's why I requested him that to explore the things.
Okay, I'm okay
Yeah.
if you use the full model, but start playing with different boundary conditions, it's not okay.
Fallas, I run it for the complete geometry. I run because you asked me to send you the full geometry, and I run it with the same conditions, and I think I get the same results that half of the geometry. So that by
Yeah.
that I can check that is correct. Use half geometry, and when you use half geometry like the one that we are showing here, you are showing here, you have to apply half of the voltage also, because the core is half of the real size. So you have to use, according to console in some documents from the library, help library, you can see that this is mentioned that if you use half of the geometry, you have to use half of the voltage in this kind of symmetry. Because you see here we can cut the complete geometry also in the plane, horizontal plane, in an horizontal plane at the middle of the windings. But there, the boundary condition that we have to use is the one that you mentioned, not the perfect magnetic conductor boundary. We have used that kind of boundaries, and it's are working well. I mean, these kind of symmetries, we have taken advantage of these symmetries, and we have good results. In this case, only we use half of the
Okay, good. That is very important.
findings.
If you get with the full model, with the half the model, select the boundaries and discretations in such a way that you get exactly the same when you run the 3D model, then it's fine.
Yeah,
That's
I think it's giving the same
that is
result.
the most important verification.
Yes.
Okay. So what is next on related to this transformer?
We can we are done with the open circuit test. We can do the short circuit test.
No, I'm asking for me.
Okay, so
Okay. If you allow me to show what we are getting, and I will explain it according to the results that we are getting with our computers. Let me show my.
So, did you get already the file from Fayaz? And can you run on your side?
No, I don't think so. I don't think so. No, I have not received it. But I run the complete geometry and I solved the.
So let me
corners.
understand something for me.
Yes,
We got this because apparently you couldn't run it, but now you're saying that you can run it.
we can run it for few milliseconds. If you allow me to show my.
Okay, go
my-
ahead. So stop
this-
sharing Fayaz.
Yes. Let me show what we are getting.
Yeah, because I am not understanding what the problem
Yeah.
is.
Let me show you. This is the response of this is no load current, as you can see. Here we are getting the currents with the considering the nonlinearity, and you can see here we have some peaks in the current. That is something that you will see in no load currents transformers, no? But the problem here, as you can see, there is a low frequency oscillation. I don't know if you can see how, for example, the phase in green have the peaks in the positive semicycle, and the red current, or the current for the red phase, is getting the peaks in the negative cycle. So we are thinking that this is due to somehow due to the maybe inrush current, because as the time is increased, this is start to move to oscillate. This response start to oscillate. I mean, it will go up, the red will go up, and the green will go down. No, and then we expect to have the response of the current. We expect to have something that is similar in the positive semicycle than in the negative semicycle, as we have observed in measurements and in the case of single phase transformers, very small single phase transformer that we also simulated. In that we can see this behavior, but not in the three phase, because we observe this kind of displacements in the current. No, we are thinking is due to the inrush current, because now we have a big core. So I believe this that the reason, but what we want to see with the bias simulations with longer times is if these low frequency oscillations stops.
So what you want is the inrush current as we have obtained.
Yeah, well,
and
we
then,
don't want to see that. Yeah.
And then let it run until you get to steady state. Is that
exactly?
I see.
I don't know if you have some.
But are you interested in the inrush, or you're only interested in the steady state?
In the steady state with harmonics, the no load current with harmonics.
I see.
That is the thing we want to see. Because let me show you something here. I cannot show you one. Let me give you.
So I was under the impression that the important thing was to get the inrush.
No, because
it's not.
no.
Okay,
No,
so I am going to ask for just to ramp it again, because then we get rid of
exactly
faster.
Yeah, because I can see that you have a big current that is the inrush current.
Yeah, but because that's what we wanted to see, according to me.
No, let me show you what we want to see. I don't know, you can see this.
We are still seeing the previous figure.
Okay.
I don't know if you're showing something different.
Yeah, I want to show you this. Let me show you what. Do you see these are measurements? These are measurements in the no load current. And this, you can see that there is symmetry between the positive semicycle and negative semicycle. And you have harmonics in mainly the third and fifth harmonic present here, as you know. But the problem that we are observing is that in simulations with the three-phase transformer, we are observing this displacement of the currents, and we are seeing only in the positive semicycle or in the negative semicycle the peaks that we are observing here. And we were thinking that this may be due to the inrush current or some components, low frequency components that are giving these oscillations. Because let me show, I think I have another more nicer figure that I can show you. Let me see if I have here somewhere where we get that kind of behavior in one phase transformer. Let me give you, let me show you what is it. Please take me 1 minute to find it. Yes. Let me see what I have here. I don't no, I think it's not. I don't have it. No, but this in that simulations we are getting what we saw in the simulations, in the measurements, in the lab measurement, but not with the three-phase transformer that's in simulations. So the thing that we are considering that maybe will will interesting for us is to run longer times in this your computer and see if these oscillations stops in some
I see.
certain time, and see if and then we can only see
All right, so
the
let me summarize it. What you want is that we get to steady state and
Mhm.
and see and see the three phases independently, right?
independent and with the harmonics, the third and fifth harmonics that usually have this kind of current, the no load current.
Okay. Fine.
Yeah, that is the thing I want to see. So I think Fayaz you can run the half of the transformer, because now I verified that the full geometry is giving the same result. So half of the geometry will save time.
Yeah.
And then maybe you can run for, we are only running for 10 cycles. Maybe you can run for 100 cycles or something like that and see if it stops.
Mm.
Because the English currents usually can stay for
But we can get rid of the inrush
seconds.
currents by ramping it the same
By
way.
ramping, yeah.
Yeah.
That's why we are.
So what we're going to do is to run your original case
Mhm.
for a longer period of time.
Yes, please.
Yeah.
Yes,
So
please. Just
let's
that,
run it for what? For a minute? That's what you wanted to run it?
well, maybe 60 or 60, 100 cycles. Maybe it can
I
be.
was thinking about 33,000 cycles. But if we
No.
ramp it, probably we don't need to go that far.
No, maybe
Yeah.
100, I think.
Okay. So
100 cycles.
start with 100 cycles and then see. Yeah.
Yesterday I tried with the 30 seconds, I guess. Yeah, 15 seconds. But it is like maybe due to the license issue. This was like this is giving me error. Yeah.
So
obviously-
what it seems to be that we're getting an error after some time, right?
Mhm.
So it runs well for
Like,
a
no,
period of time.
No, sometimes this is running fine, but license is like on is like if some other, since this license is floating, right? So if it is taken, then it suddenly license error is there.
So, but that is our problem. That is not that is okay. All right.
Yeah.
So
Professor, let me show you. This is the result that we consider that should be. I mean, as you can see here, there is a symmetry between the positive cycle, semicycle, and negative semicycle. This is simulation also, but this is for a geometry of a one-phase transformer. And here we can see the behavior that we were expecting to see.
Okay. Yeah.
This
Now,
kind of.
but this is never going to match the measurements because
No, yeah, but unless if we see that the trend that we are observing in the third harmonic magnitude that is decreasing when we have a short circuit with the turns, we can say that is it's giving an idea that is correct.
Here you don't have hysteresis, so this is not going to be the right way. You're never you're never going to reproduce
exactly
your measurement unless you model the same thing. I mean, you need to put hysteresis too.
Yeah.
Okay.
Yeah.
So, but we'll do this. We'll do this now. But then, can you produce a hysteresis curve of this transformer, of this material, or not?
I think the BH curve that they are considering is not considering the hysteresis. It's only
Not exactly. So,
no.
but you have the transformers. Okay, can you test it?
Yeah, we can test it. One of the three-phase transformer, yeah, we have it physically.
So because we should extract if you want to reproduce the measurements exactly, then we need to use the exact steel, right? Otherwise, we are okay. We can do the simulation. That's no problem. But when you come, let's do it by steps. Let's do the simulation and compare it with the measurement. And if it doesn't work, then we have to improve the model.
Improve the model.
Yeah.
Yeah, yes. I think that we want to see
Fine.
what.
Rather than being just working crazily, let's go stage by stage.
Yeah.
Yeah. All right.
Yeah. So that is the idea to run for longer times and see what happened with this low frequency
Okay.
oscillation.
Fine. All right.
Yeah.
There you go.
Thank you, Professor.
Okay. Now, today, what I wanted to talk about is about the thermals. I want to talk about the thermal behavior. As we discussed briefly previously, no machine is designed only electromagnetically. So all machines need to be the thermal behavior is what is the most not the most important, but it is the factor that determines the rating. Okay, all right. So I am going. Oh, I need to share the screen. This recording is there. So what is missing is that I share my screen. And where do I share it? Where do I share it? Zoom. Share. Okay. Okay. So I hope this runs things right. I have a big problem now. It doesn't write. Let me see. It doesn't want to write. Sorry, let me go and get the other one.
I have questions regarding the multiple. Yeah. So maybe at the end we will discuss.
No. Not even my finger is writing. So what is the problem? I have a problem here with my computer.
Maybe restarting.
Maybe what? Not even my finger writes, you see?
Oh, it's working. It's working.
No, it's not.
Yeah. It's
It
working.
moves, but it doesn't write.
Then you haven't choose the
It's been,
pen?
look, I'm choosing the pen.
Just restarting.
Restart. And look, with the mouse, it writes. With the mouse, it writes, but I cannot teach the class with them. With that. Oh, let me see. No. This one doesn't work. This one doesn't work. This one doesn't work. My finger doesn't work. Well, let me get out of this program and run it again. Let me get another class. This is not what I want, but what about here? No. No. I have 3 pens and none of them work, and not even my finger.
Bluetooth is not connected for
My Bluetooth is not connected.
the pen and Bluetooth.
No, but the finger, what's wrong with the finger? There is no Bluetooth with my finger. Yeah. So,
Oh my.
How do I do now? I became paralyzed when
You said restart your.
restart the computer. So you guys are gonna lose me because I'm gonna restart the computer.
Hello, can you hear us?
Let me start with.
Yes, yes.
Oh, so they were not disconnected.
Yeah, they are there.
All right. Now let me see. The first thing I need to do is to try the program. Right? Journals. Journal here. Okay. Tell them that it's coming.
Sorry, what was right?
Tell them that it's coming.
Yeah, so yeah, we are coming back in 1 minute.
No. It's coming back, but it's not. It's just not what. It wasn't. Finger doesn't even work. There's something went wrong with the computer. Nothing. Nothing.
Maybe the batteries and fans are like dead.
No, but my finger doesn't work either. Look, my fingers should be able to write.
So
You can check that. Maybe there are some options of screen
Options.
in settings.
Settings.
Touch screen. There should be some screen.
Where is the screen? System,
Yes.
display. Identify. No, it's okay. Duplicate. Then scale, display resolution.
आपके पास है क्या फिर? हाँ तो
Let me disconnect this.
एप्पल वाला नहीं चलेगा.
Okay, you have a way to write? Okay, but you need to connect it to the Zoom.
ब्राइट स्पेस में जाओ, उधर रीडिंग्स में आप एडिट हो. हाँ, तो रीडिंग्स इलेक्ट्रिकल में जाके जूम पर क्लिक करना है, ब्राइट स्पेस में. स्वेटर पहना तो गर्मी तो होनी है ना.
Oh, I see. So please be patient. My computer is suffering complications. And then we'll change into an iPad or something.
No
Is it
problem.
an iPad?
ये क्या करना है?
ब्राइट रीडिंग्स में गए ना, रीडिंग्स में है इसमें जो इधर का कोर्स है, इधर रीडिंग्स में एडिट हो. ये जो कोर्स चल रहा है इसमें एडिट हो, ये वाला रीडिंग्स, ये वाला इसमें रीडिंग्स में जाके. हाँ हाँ, इसमें फिर जूम में इसको जूम को
प्रेस कर सकते हैं. ठीक है.
हाँ, इसमें ज्वाइन. हाँ, इसमें आप आ गए.
No, you need to share the screen too.
फिर क्या करना है?
इसमें आ गए. ओके, शेयर स्क्रीन करें. मैं यहाँ से स्टॉप करूँ.
Give this to you. You are the projector here.
Okay. Share screen. Yeah. From here.
Okay. Make it bigger, I guess. It's ready? Yeah, let's see. We need to mute you.
Yep.
Okay. No. No. Can you hear us? Can you hear me?
Yes. I can
Okay,
hear you.
so sorry for the technical difficulties, but
No problem.
so machine design, actually machine rating, it is determined 100% by the thermals. So whenever you hear that a transformer, a machine or something is 500 kVA, for example, that has nothing to do with the power of current or anything. It really has to do with the temperature of the hotspot. That is what determines the, double like this, I see, and then, very good, not so bad. So now I need to, how do I scroll down? Just scroll down like this? Okay. All right, so it's the temperature of the hotspot. So if you have a transformer, this is your transformer, and you have, let me make it a 3D transformer, and you have a winding here. This is your winding. What determines, let's say that is an insulation class that it is a 105 degrees, 105 degrees C. This is the insulation class. So 105 degrees C. What we're talking about here, the hotspot, is something that is going to happen in here. It's going to be, if I see it to this from the top, if I see this from the top like that, this is the winding. It's something that is going to happen somewhere in here. Oh, let me put the red spot, the red one. It's going to happen in there, in the winding. Actually, it shouldn't be there. Let me erase, delete this. How do I do undo? Okay, like this, like this. So it's going to be in the winding, in the inner part, close to the middle. Say this is about 1/2 of H here and 1/2 of H. It's going to happen there, depending on the cooling and things. And this is what will determine the actual rating. It has nothing to do with current and power. We rate a device. Let's say you have a 3-phase device, and it's rated for 150 kVA. Whatever these devices could be, a generator, a transformer, a motor, you name it. And it's 150 kVA. What really means is that it is single phase 50 kVA, because you can't put on this machine that I'm going to put here, you can't put on a single phase the entire load. So I cannot come here and say, this is 150 kVA, right? But a 3-phase machine will tell you, oh, it's 150 kVA. So this assumes balance operation. So what really, really matters is the temperature of the hotspot. So we as machine designers, we need to look into the thermals. So thermal behavior. There is 3 mechanisms to, okay, let me change this. The whole point, the whole idea of this is to have energy gains equals to energy loss. So when this happens is that we have some balance. Okay, so energy gains in a transformer, let's say, will be resistance, current square. That's the resistance of the winding, currents in the windings, plus losses in the core, right? And are there any other losses in a transformer? There could be, depending on the size of the transformer, there could be dielectric losses. Okay. Now, this needs to be equal to the heat that is dissipated. Heat is dissipated for three mechanisms. There are three mechanisms. Is heat dissipated by conduction, plus heat dissipated by convection, plus heat dissipated by radiation. Okay, so there's three mechanisms only. And the three things happen in simultaneously, but they don't happen everywhere all the time. So conduction is the easy one. So conduction, oops, no, 1, 2, okay. Yeah, conduction. Conduction is you have a heat source. This is a heat source. You have a material here, and you have here the way the heat is dissipating. So by conduction is exactly your Ohm's law. So I need another color. Oh, I see. Thank you. So how is the heat going from a hot place, hot side, to a cold side? And it's always, the heat always goes from hot to cold. So how is this conduction? No, in conduction, we used to say that we can always go through an electric circuit. It will always be an electric circuit because the heat, the heat transfer is always equals to some resistance, which in thermal, we put it like T, thermal resistance, and given by the current, the heat transfer is equals to the resistance times the energy. So as you can see, it's very similar to Ohm's law. So energy, yes. So the energy we will represent almost always by a current injection, and the thermal resistance like that, and then we can close the circuit if you wish. This is because I have a very simple thing. So the heat transfer is equals to the temperature times, this is the flow, the heat flow. Heat flow. No, what am I doing? No. The temperature. I'm going to call it T is the temperature. The temperature is the thermal resistance times the heat flow, the heat. Okay. So this is the heat. And this over here will be the temperature. I'm going to put it here, temperature. So this is the simplest of all mechanisms of energy of heat flow. It's just like a resistance. And this happens in the windings of transformers. Let's say that you have the turns here, turns there. It will happen between the layers of the insulation here, between the layers of the insulation. It will happen in everything that is in contact with it. So this mechanism is called a contact. So when you have physical contact, this is how this mechanism goes. The next one I want to discuss is the radiation. Yeah.
T is the temperature.
T is the thermal resistance. This is the thermal resistance. Thermal resistance.
And heat is the heat flow.
Heat flow, you can say, is an analog to the current. And the temperature is an analog to the voltage. So if you have a system, of things, for example, this could be, you have a resistance there, you have another resistance there, and another resistance there, depending on the layers that you have. You still have a heat flow here, a heat generation, and here you can measure what is the temperature, right? Now, if your windings are creating heat, you can have a circuit like this, right? Each one of those windings can have, or each one of those turns can have its own heat being produced. And of course, if you do it with a little bit more of refinement, this current that we call it the heat, let's say heat 1, will be equals to the resistance, which is a function of temperature, times the current square, right? The current that is circulating, electrical current that is circulating in the windings. So let's say this current, okay? All right, so each one of them can have a different value because this one, H2, may have a different resistance. This has resistance 1, temperature 1. This one has this H2 will have a resistance 2, which is a function of temperature. The current may be the same. The electrical current may be the same if we were doing it in a steady state. If you're doing it into a transient, then the current may be different because of capacitive effects. But normally, heating from a transfer is not, from a transient is not important. It's a steady state what matters, except the sole exception is short circuit. All right. And each one of these sources can have a different value. In general, this thermal resistance 1, thermal resistance 2, thermal resistance 3, in general, the properties of these materials don't change. When it's in regards to electrical machinery, the insulation doesn't change its thermal resistance. It also doesn't change much with temperature. It's insulation, electrical insulation properties. All right, so this is the first mechanism, and it's typically represented by an electric circuit. Of course, you can write this in equations, but even the mechanical engineers and everybody who has to deal with thermal goes to an electric circuit because we have already built programs that can deal with the insulation, with the electric circuits. And this is basically a DC circuit. Okay. The next one, which is not typically the way it is explained in books, but the next one is, I'm going to go with radiation. But I go with radiation because it's the next simpler to explain. What what's the problem? No problem.
I was asking him that in the cables, the
Resistors.
resistances are in parallel. Here we are.
No, everything is in series,
Like the concentric.
in parallel, in series.
Capacitors
So let's there is an interesting thing here. It's an interesting question here because it's a practical value for us. So we have a cable that has multiple layers. And I am gonna draw it just a little bit exaggerated. So this is the conductor, right? This is the insulation. This is the screen. And this is the jacket. Let me not call this a screen. Let me call it the sheath. Thank you. Sheath, and this will be the jacket. Okay, so the heat is mostly produced in the conductor. So the heat wants to go out, right? And so the conductor, I will put here, this will be resistance of the conductor, current square of the conductor, mostly. The resistance is temperature dependent, but let it be there. Okay. Right, so that Fayaz is happy with the resistance of the conductor, which is a function of temperature. Okay, now, the next layer will be the insulation. So I have here the resistance of the insulation. Now, there is in series the resistance of the sheath. I will put here temporarily the resistance of the sheath. And ideally or theoretically, you could also put the resistance of the conductor, but the conductors can be assumed that they are so high, the thermal conductivity, that we don't even need to consider it. So I will erase this thing and leave it the temperature, give me 1 second, temperature of the jacket, yes.
But we do consider DC resistance. DC resistance when we calculate sheath loss factor.
Okay, I'm talking right now about thermal resistances, T, no R's, no losses. Okay, in 1 second, I will add your question. Now, here we will have another source of heat, which will be the heat coming from the screen, from the sheath. The sheath. And then I get to the external of the cable. So here is the temperature of the jacket. But then I have another resistance, which will be the thermal resistance of the media, of the medium. And in the end, I will have ambient temperature. So this is your model, is over here. So you have the heat coming from the conductor that is, let's say, its free circulation is impeded by the thermal resistance of the insulation, the thermal resistance of the jacket, and the thermal resistance of the medium. Now, but there is another heat source, which is the current source, or another heat source that is due to the sheath. The sheath, you will, in cable and capacity calculations, this heat from the sheath is considered with a loss factor and the current of the conductor, a proportionality factor for the current of the conductor. But in general, I don't even need to, I probably, this is a bit too much because it's too specific. For every case, there will be some heat coming from that. All right. If you have heat coming of different layers of different components, you need to consider all that heat. In cable and positive, we do it through a loss factor to make life easy. But that's not what we need to do in general, right? It's very specific. So if you had a transformer, let's say, if you had a transformer, I'm going to put a single phase transformer. With only one, let's say a set of windings. You have this thing. Let me make it thicker, right? And then you have another winding over here. You have another winding over here, right? So the thermal behavior, the thermal circuit of all this would be, I get the inner, this will be the a current source for the core. Then there will be some thermal resistance of the insulation, core winding 1, core to 1. Then I'll have the heat loss coming from the inner winding. So this will be winding 1. Then I have the insulation between winding 1 and winding 2. Then I have the heat source coming from the winding 2. And then I have the thermal resistance between winding 2 and, let's say, oil. And that would be it for this, right? So in here I have three heat sources, the core losses, the winding 1, winding 2, and I have 3 thermal resistances. Now, this transformer, this normally this is not just there. It's either in oil or in air, right? So up to this point, I am, let me see, temperature of the fluid. And I will deal with the fluid in a moment. Okay. Before getting into the fluid, into the actual fluid, I'm gonna go with the second mechanism, which is radiation. Radiation. So any body that is hot emits heat to another body by radiation, simply. Like you can simply see, I mean, if you have a surface that is hot, you can see that it will emit a heat to the to another body that is nearby by radiation. So there is no contact, but simply because they are relatively close, there is a radiation coming from there. So this radiation happens between most times in a transformer, happens from the tank to the environment, right? That's a typical thing. So that way you call it a radiation free, how do I call it? Free, there is a name. Surface to air radiation. Yeah. So this radiation has the way we normally say is we compute the thermal resistance of radiation, which has an H, and it has temperature hot minus temperature cold, but these things go to the power of 4. And this H has to do with the emission coefficients. And sometimes for certain arrangements that are not completely to the air, you will have that the temperature of radiation is equals to something that is called a view factor, T hot to the 4 minus T cold to the 4. This is called the view factor. So this view factor has to do with, for example, you have a sphere, right? That is emitting heat.
It's working.
It's working now? How do you fix it? It's not working.
It was working.
Okay, let me this one.
Maybe you have to change your batteries.
Okay,
Maybe I can bring a battery.
these batteries are special. Okay, so another type of radiation is not to the environment, but it is, let's say that you have a surface here. You have a surface, a flat surface somewhere there. And it's flat, but it could be any shape. So the view factor is this. The view factor is this thing. So I have a sphere that is emitting heat, and how much heat is going to get to a body that is nearby, it depends on the view factor. So the view factor is out of the 360 degrees, how many degrees you have here. So this theta. Okay, so most of the times, the complicated part is to determine the what? It's not writing? Scroll. Well, I am writing up there. Okay. All right. So radiation is relatively simple. The only thing is that you have to make sure, or the important thing is the temperature is to the power 4, right? So, which means if you have temperatures that are near each other, there is very little radiation. But if you have a temperature that is, the temperature difference between one and the other is very large, you will have a lot of radiation. So to the power 4, right? Okay. Now, the most complicated of all of the heat transfer ways is convection.
Sorry to interrupt you again. So what's that T hot?
The temperature of the hot surface.
Hot surface.
Yes. This is surface to surface.
No. That's temperature of a hot surface, power 4 minus temperature of cold.
Of cold. Cold. Fayaz, you need to go and take Greek 101. Temperature of cold surface.
Wow. It works, but it will stop.
Okay, so let's leave it there.
Because we don't have batteries.
Yeah.
No.
Okay.
Now it's working. I don't know when it will stop.
Let's continue this way. All right. Convection. Convection is complicated. It has two modalities. Laminar flow, and turbulent. So I put a very ugly R. So is laminar flow or turbulent? In general, laminar flow refers to low speeds, low flow speeds, low flow fluid, low fluid speed. And turbulent refers to high speed. Let me explain it with a pipe, right? I have a pipe. So through this pipe, I put here a fan that is blowing air into the pipe. If the speed is slow, this is going to go just, oops. This is just going to go like that, like that, like that, and it's going to come out in almost the same way. There will always be some resistance on the edges, right? Around the edges, there will be some resistance. And if you were to plot the speed of this, let's say this would be radius, the radius from here to here. The radius, it will be something like that, right? And this being the radius A. So this would be A. So your curve would be something like this. Of course, when it's touching the surface of the pipe, there will be nothing. But it's pretty uniform in the center, and as you approach the end of this pipe, it will be different. Now, this is, of course, when the wind speed is relatively slow. If you increase the wind speed or the speed of the fan, right, now you have the same thing. But now this goes much faster. So now this was rotating at this speed, and this one we rotated at a very accelerated speed. So now the wind is going there very, very, very fast. So when you blow into something, just put your hand in your mouth and blow slowly, and you see that it's coming at a regular laminar flow. But if you blow hard, the air itself puts resistance to the movement. The molecules of air that are here are going to be excited, but they don't want to move from there. So they will give you circulation, turbulence. Okay, so still some air is going to come here, but it's going to come in very irregular ways. So some air is going to go there. Now, turbulent is more efficient than laminar. So this is laminar, and this is turbulent. So when you compare this versus this, of course, the turbulent way is a lot more efficient when you are transferring heat than the laminar way. Okay. Now, the way we normally process this is we also come up with a T, a resistance for thermal resistance for convection. And this is always given by a complicated heat transfer coefficient, normally is lowercase h. Lowercase h, and a function of this is temperature by convection, and it's a function of a complicated function of speed and other things. Okay, so this and this in normal, let's say, heat transfer books goes through the crazy things of a Reynolds number. What are the others? What are the others?
Pressure. Reynolds Nusselt.
Reynolds Nusselt. Nusselt number. There's another one. Grash. I don't know how to spell it. Graph. Okay, it doesn't matter. What the mechanical engineers have done, because all these things, all these mechanisms, in particular convection, is extremely complicated. So what the mechanical engineers have done experiments, many experiments. So have done experiments for most geometrical arrangements. Of course, they have taken up cylinder and they have pushed air this way. Okay. They have also put the cylinder like that and push air that way, right, around it. They have done the same thing for flat surfaces, for basically any number of things. Of course, for pipes, they have done it for round pipe, for square pipe, so they have done it for we cannot erase anymore.
Okay. No, it's
I'll go to the eraser. Okay, thank you. Okay, they have done it for circular tunnels. They have done it for square tunnels. They have done it for a lot of different arrangements. And then they come up with something that is called an average model. Okay. Now, because we are not talking about analytical solutions, but we want final element solutions. So we don't need to worry about all these crazy things, except that sometimes, because of the complexities of the heat transfer mechanisms, the program sometimes uses approximations. So if you go to console, to the heat transfer modules, and I'm talking in particular the console, and I will believe ANSYS is similar. You have to define your physics. So you need to say, okay, I need conduction. I need radiation. And I'm going to ask you what kind of radiation you want. You want surface to air or surface to surface? Surface, I don't think it's called air, it's called a, I won't put air, but I will check what exactly is. So it's surface to surface radiation, surface to air radiation, and then the complicated one, the convection. In here, there are many, many models, but at the very least, you need to deal with the laminar or turbulent. at the very least. Now, there are several other complications in here. Because the problem is not highly nonlinear. All this is nonlinear. You can see the radiation is to the power 4, nonlinear. It's not synchronized.
Takes a little bit.
Oh, yeah, I see. I am the one. The operator of this lab.
Because this comes through this.
Yeah. The operator of this tablet is not very good. Okay. Okay. So it's highly nonlinear. So you will have to solve the problem with the different solvers, saying how do you want to deal with in addition of to the discretization, how do you want to solve this? Which engines you want. So you're going to have to pick the solvers become very important. So if you want a time domain modeling, if you want steady state, so that's the other thing you need to do is transient versus steady state. When we started using COMSOL for thermal things about 15, 16 years ago, the battery is running low. Oh no, it's fallas. Next. Okay. So when we started using COMSOL about 15, 16 years ago, they say that the steady state engine did not work. Did not work in general. There were very specific cases for which it ran. So COMSOL forced us to use the transient for everything. As far as I know, today this has been fixed. So today we can say that this is fixed. And now you can get a very efficient steady state solution using COMSOL, and you don't need to go through the transient all the way to get to steady state. So we have been very successful with David, which will come next class and present a lot of the things and tell us how to set up things on this thing. So we can do now steady state or transient, and we have seen that the error is very small between one of the others. I would say I have seen 1%. Now, in the thermals, it's very, very important that you select the right meshing. For electromagnetics, it's okay, but it doesn't make a huge difference. But thermal solutions may take 2 or 3 weeks, even in a very powerful computer. So it is important. It is important that the meshing gets done correctly, and the solution of the problem is obtained with the right solver. So important is the meshing. Important is the meshing and selection of solver. All right. Okay. I don't use the program, so I don't know how to set up a case or anything. You use it. You use the thermal. Have you used the thermal?
I can show next week.
Next week will be David. Can you show it now? No.
COMSOL not working.
COMSOL is not working, but that's for electromagnetics, right?
No, I cannot do this. It's not opening even.
Oh, it's not opening?
Yeah, it's open, and when when we get clicking it drawn and it's not. It's
Okay. All right.
Next week will be good.
Okay.
Is there any research on this topic? Like, if we are taking out the heat from the conduits of cables, so that the fan which is blowing out the heat from the conduits of cables, it keeps the flow laminar.
Why do you want to keep the flow laminar?
Because the laminar is the best one that can take.
No. No. Turbulent is much more efficient than laminar. So
above certain speed.
So after certain speed, there's always turbulent flow.
Yeah. They blow it a maximum?
No. Let's talk about a transformer. This is a great question, Kashif. So let's talk about a transformer. Let's see what happens inside of transformer. Inside of transformer. And we're going to do some sort of a cut. So we're going to have this being cut, right? And we're going to have a winding. Let me put the winding in blue. From here to here, this goes this way. This goes this way. I'm just going to put one winding. Over here, over there, over there, over there. But this transformer may have a tank, right? It can have a tank. Let me put the tank in some other color. What other colors do I have? In gray? Oh, I have all the colors. Thank you.
You can also swipe if you want more colors.
Oh, all right. So let me get brown or this one. All right. So I can have a tank. Oh, this is the same color. It's not. I want some other color. Say that one. No, this becomes too thick. So the operator is still not confused with this. So give me the green. Give me green. All right. So it can have a tank here, right? Not only it can have a tank, this tank may be connected to a radiator, right? There could be a radiator over here with fins and things, right? So it can have a radiator. And it can also have fans in here, right? Here, it can have a fan and 4 fans, let's say, on the radiator, right? And it can have also an oil pump, right? This is full of oil. This is full of oil, and I can have an oil pump. Let me put the oil pump here, right? A motor here that is pushing the pulling the air, the oil there. And the oil now is going to go, let me see, what color, what is a good color for oil?
Black.
Black? Yes. Black. Okay, so
Use what?
Is pushing the oil this way and this way. So we have a complicated system, right? So, transformers could be natural convection. It could be forced convection. They can have the natural oil, natural air, force, natural air, force oil. I don't even remember these names. Natural air, natural oil. I used to remember them, but I don't know the names anymore. Onan, yes. Yeah. Let me see. No,
No.
Oil natural, air natural. Yes. And then it could be, this is natural. It could also be oil, force, natural, air. Or it could be oil, force, air, force. I don't know if those are the names, but if they are good, if they are not, well, you know what we're talking about. Okay, so, and that depends on, even on stages. Some transformers are rated for different values. So if it is natural, let's say, if everything is natural, maybe this transformer is 100, let's say. 100 megawatts or mega bars, mega MBAs. And if you have forced oil, maybe it's 125 megavolt amperes. And if it is this, maybe it's 150. And if you have one stage of fans or two stages of fans, you can increase the rating. Okay. You increase the rating. There is always that you increase the rating, there is a reduction in efficiency. Okay, for several reasons. For example, you increase the rating, therefore you're going to have to do something. So somebody needs to pay for the oil motor to move. Somebody needs to pay for the fans to move. So the total efficiency, power in versus power out, is different. So, but the whole thing, what determines what is the actual limit of this is the temperature of the hotspot. So how much is the temperature there and there and there and there and there and there? So is the hotspot temperature what matters, right? Hotspot. Oopally. No. Yeah, I know what I don't know what I did, but I want to go this way and use the small one, right? Okay. And I want to get the black. Okay, this is the black. So temperature of the hot spot. So that is what really matters. That is what, if you burn the insulation in some little spot, the whole transformer is out. Now, manufacturers have a lot of experience with measuring this, but they have models for their things, but performing a full final element for a big transformer, it has oil, natural oil, forced oil, forced ventilation in a 3D model final elements has not been done yet. For a big transformer, it's still not possible. So
there are some other methods.
I can show you some of the things that I have done with I have done things. Oops. So I don't know if I'm connected to the web. Am I connected? I am not connected. So just give me a minute so I can connect to this and show you some of the things.
People have done for the tank, not for the
Oh,
windings.
no, I'm going to show you. We have done everything for the tank and for the windings. But the problem, it has been that it has to be done by parts. We have done it by part 3D. I'm going to show you. I'm going to show you the, maybe, yeah, maybe I don't need to show it from here, right? Let me see. Mm. Here I go to this guy and a zone. Today start. Why am I starting it again if it has been already there? I should have put join, huh? Did I join? Let me change this and go to join instead of start. I don't want to break it. Oh no, I have to do start.
Then you stop sharing.
Yeah, I'm searching that option. Where's that stop share over here?
Oh, I can always kick you out from the share. Put in mute.
Okay. But this is already made.
Yeah. No, it's not mute.
No, you're.
It's yours.
No, this tab. Tab has to be muted.
Okay. No.
Okay.
It's Fallas. Of course it's Fallas.
No.
So I put here. Okay, so we leave it like this. Okay, so for example, we have done a few things like this. Files, office, papers.
Yeah.
Make it a full screen. Double click on it. Yeah, double click.
It's not coming out.
Jaime, Julian, Juan
Just
Martinez.
close the right bar.
Let me call here
I'm sorry.
transformer.
And zoom.
Oh, I see.
You can zoom it. Double, yeah.
Let me do. I'm gonna show to Jose. And
Nothing fine for us.
I think it's fine as long as we can see it. It's fine as long as we can see it. It's fine as long as it's visible.
so we have done these things. I hope it opens in this. So what I wanted to show is the figures, is these things, right? Let me see the flow. This is the heat. We are operating a transformer in a funny way, and we are doing all the thermal analysis. But the transformer, this is part one, I guess. Part two. So I need to get part one. Part two, part one. Yeah. Now, part one, let's start with part one. So what we have done is all this. So this is the movement. This is the movement of the oil, right? This is how it moves. Oh no, this is the flux. This is the flux, zero sequence flux. And then we of course have a model, but the idea is that we have created a thermal. So this is for a real transformer. This is a transformer that was tested in Spain. And these are the characteristics. So it has to go to part two. All right, here. This transformer has, as you could see here, this transformer has a radiator, right? It has a set of radiators that you see here on the right. But it was really impossible to model this. We could put it in 3D in a supercomputer, and it was just impossible to do it. So what we ended up doing is to model the transformer without the radiator. So we remove the radiator and we push the oil in and out. We wanted to find the hotspot for this funny operation. So this transformer is a Y grounded, Y not grounded transformer. So which shouldn't be, right? Typically, Y grounded to Y not grounded don't exist, those transformers. Typically you put a delta or you ground the Y, but then you increase the short circuit currents. So, but we said, what if we can do it? So we did all this thermal analysis, but we couldn't do it with the radiator connected. So we put temperature in and temperature out of the radiator. So we put oil out into the radiators, and we just non-model the radiators, and we assumed that the radiator was going to cool down the oil so much and push it back into the lower part of the transformer. Okay, so, but these sorts of things we have done. Now, I don't know if I'm going to find the paper from...
So if we have the sensor placed inside the transformer, outside the transformer, and then take...
Normally, manufacturers of big transformers, they embed a fiber optic with a winding. A very thin fiber optic goes embedded in the winding. And they have the actual temperature distribution of the windings obtained with fiber optics and a laser. So they do these things. In a cheap, that's for a very expensive transformers. For a relatively cheaper transformer, you just go next to the core, right? You slide the optic fibers next to the core rather than following the winding. And for a cheaper transformer, you only measure the top oil. Yeah. And through a model, I'm going to see if I can find the model. We have a nice model for that. Okay. So you measure the top oil on a relatively cheap transformer, but not distribution, not too cheap. A power transformer substation, you will have measurement of the top oil at least. Yeah.
Do we have these data available?
What's that?
Do we have this data available publicly, or do you have the data?
We have the data. We instrumented a transformer here.
Do you have it?
Yeah, I have it. I'm just going to find for the paper. I'm going to look for the paper. We created a beautiful model for this. The only thing is I don't remember where this paper is going to be.
What will be the variation between core and oil temperature? Usually,
the hottest spot is in the conductor, in the copper conductor near the core if there is no cooling ducts in there. If there is a cooling duct, then it's pushed a little bit to the winding, to the inner of the winding. But if it is not cooling ducts, let's say you have a roundish core, and then you insulate it there, and then you put the winding on top of it. That is the point of the hotspot, in the middle, or kind of in the middle. Yeah. Let me see, Julian. I don't have Julian here. So I think I'm going to go to here. So the IEEE Explore, it's going to be much easier. It's going to be much easier to find it here. So it's going to be Sandras, author, Julian Sandras, applied. Great. Okay, validated heat transfer model. Then I got the PDF. Great. So in this paper is a heat transfer model validated with a bolt here, like in Metrotech, right? So this is the model that we proposed. So it's heat gains, heat losses. So this is, let me see if I have the figure. This is the figure. So a transformer is inside that bolt. And the transformer occupies almost all the bolt, right? As it should be. Okay, so the transformer has these 3 phases there. This is a network transformer, so it has a network protector on the top. And this is not force ventilated. This is natural convection all over. Okay, natural convection is the most complicated of all three ways of convecting. Okay, so we had the dimensions of the transformer kind of estimated, kind of we knew a little bit, but we couldn't say we know. We just cheated saying these are the ways it's normally done, and we got the dimensions right because we had the dimension, right? So this is the model. It's nothing but resistors and capacitors, because some of these things have great inertia. And some of these things are nonlinear. For example, the convection is nonlinear, radiation is nonlinear. So we created a circuit model, and we instrumented this transformer, and we got very good results. So the error, as you can see, is very small for a year-round measurement. That's what we did, entire year. It was more like 13, 14 months. So started in August and stopped in August. So it's 1 year. As you can even see, the times when this transformer was disconnected, the temperature drops. Yeah. So we have this is simulations, and the others are measurements. Times measures versus simulated. Okay. We have the loading, we have the measure, and the absolute error, as you can see, is never more than 10%. And there is a region between June and July 2011 where there was no information. The device stopped reporting the measurements. So at that point we didn't have, but it captured, again, very nicely. So that's and this model is simply based on these equations. You see, the Nusselt number, Reynolds numbers, and these crazy little things. So it actually worked. At that point, we didn't do a final element simulation of this because we had the little piggy there. We could just measure the little piggy. So otherwise, we would have built a model. Mind you, this is 2011. That is 13 or 14 years ago. And the research is always done a little bit earlier. So we couldn't solve it at that time. Even in final elements, most probably we couldn't get the transient and get all this thing done. We had a very powerful server and very important things, but still, both things. We didn't have access to the supercomputer, I guess. No, we didn't, because we joined NYU in 2014. So we didn't have a supercomputer. We had a very nice server with 48 cores, and it was great, but we couldn't do it. So we presented this model to Con Edison. Con Edison, for the Mexicans, is the Compañía de Luz of Mexico City. So that's what Con Edison is the power utility of New York. And they say, I don't believe your model. Don't believe it. So we are going to instrument the transformer. We give you the loading, we give you the things. And because we don't believe you, we instrument the transformer and see. And we match very nicely. So
how do you capture the nonlinearity? What are
the nonlinearities in this model are all modeled through average models. So Nusselt number, Reynolds numbers, and in all this, the flow was always laminar because there's no forced ventilation. So it was always natural convection. But natural convection is the most difficult of all.
The nonlinear resistance in your model, it's a function of what parameters?
The temperature, pressure, pressure. That's it.
Temperature and pressure. So
yeah.
What pressure have you taken?
Normally the pressure the local pressure you take, we are in New York at sea level, you take that base. But the pressure of air changes with temperature. The density changes. So if the air is hotter, it's less dense.
So you took average monthly temperature?
No, we took the ambient temperature of every hour.
Every hour.
Yeah.
And then take an average of whole month.
No, never average. We did point by point, transient. Never took any average.
It is hourly spaced.
This is probably 15 minutes.
15 minutes. Okay.
Let me see. No, all the mean is going to be, let me see, hour.
Time step.
Recorded several
Oh,
times.
the average citywide hourly temperature, ambient temperature. It was an hour. It was an hour resolution. Yeah. Yeah. So
And how you decided the fixed values?
how do we decided to fix what?
Fixed values, which are fixed, like capacitor over there.
Oh no, we the capacitor and the resistors that are fixed, that don't change, like the conduction resistors, they depend on the geometry.
Okay.
So we build a model like this, right? We build a model like that.
Was air ventilated?
It was, yes, natural by itself. Yes.
No.
No oil inside, yes.
Oh, okay.
So the transformer, this transformer is a 2 megawatt transformer.
Oh.
It's 2 megawatt transformer, typical of the installation. I mean, just walk outside Metrotech and just see a grill that looks like that. And inside that, there is a transformer. So those grids where the dogs shit, those are transformers, right? You've seen them. All the dogs.
I always see like these.
I've seen those, and then when I look inside, sometimes it's empty,
No, it's like a big transformer in there.
and sometimes it radiates, gives off.
Yeah,
It gives you heat because there is a transformer in there.
No,
I
it makes
thought this
sense.
heat is coming out from the metro
Train.
train.
Yeah.
Sometimes, if the grill is due to the subway, yes.
Okay.
But if the grill is where there is no subway,
Okay.
it's a transformer.
You never know where the subway is
All
passing
those prevent
underneath.
Yeah.
Because it's a lot of mesh around the
Yeah.
Manhattan. And
Yeah, but if you're in Brooklyn, you see where they are. Yeah. Let's say if you go to Flatbush here, you know that the subway is there. But if you go to Metrotech, you know that there's no subway there, right? That's a transformer. It's a transformer thing. Yeah. And it's full of dog debris.
Yes.
how they prevent water and
They don't prevent, they want the water. The water cools the transformer. The water cools the transformer, but it also corrodes the transformer. So all these transformers are to be operate submerged. So
but there should be some way out, or there should be
there is a way out of the water, yes.
Otherwise it's
But no, the transformers can operate submerged, no problem. Submerged 100% in water, no problem.
we had our transformer, I mean, that went out because of water in our power plant
Where?
in Pakistan. Newly built power plant.
Well, but here, no. The transformers are submerged. So they can just be full of water, no problem.
I think waterproof.
Waterproof, but it's more than waterproof. Waterproof is when it rains and it doesn't damage it, but it's submerged. It's a different NEMA class. Yeah, I think waterproof is NEMA class 8 or 9, and these are probably 12 or 13. I don't quote me on that, but that's a good guess. It's not a completely bad guess.
That's a lot of money for utility.
It's a lot of money for the utilities, but there is a lot of money in New York.
There is a lot of money in that also
Yeah,
make your profits high.
exactly. Utilities make money as a percent of whatever they sell.
Yeah.
That's why do you think it's so expensive, the electricity in New York City? You see, yeah. How much is the cost of electricity here? 30 cents?
Yeah.
In New York City per kilowatt hour.
I think it's more than that.
No, it couldn't be that much more than that. It takes 3 cents to generate it. 10 times that, I think, is good enough. All right. So let me take over here. So let me stop share here and continue with this. I'm sharing already? Yes, because it's through I can see it through Fallas. Okay. So as I was saying, the most complicated mechanism is natural convection. So let me even go to a little cable. You have your cable here that is producing things that is producing inside a duct. So what is going to happen here is that the air is going to start to circulate here, and it's going to create a plume right there. And then this plume is going to go to one side or to another side, or if you're very lucky, is symmetric. But most times it will not be symmetric. So this is the circulation of air. It is, these kind of things are very difficult to model. So these things are chaotic and random. Yeah. We will see. We will see some of the examples. I have a few. I have some examples on the thermal fields, but I prefer that David will give us some good things, and also helps how to set up a case and those things, right? So next week there is no time anyways. So next week I will make sure that David is back here and tells us about all the thermal secrets that he's learned over the past 10 years or so. Okay. Thank you for letting me use your iPad.
Mhm.
So stop sharing, please.
So I need to.
Any questions on in here in the room or online?
No, thank
No
you.
questions for me?
No, thank you, Professor Leon.
Okay.
For the cable model.
So we'll see you next week.
I have a question.
See you.
You
Thank
design
you.
a
Bye.
transformer for natural convection. You want to design it.
See you. Thank you. To external laminar flow, yes,
Why? If turbulent is more.
because natural convection. You need speed. How are you going to get the speed?
But it also depends on the size, right?
It doesn't matter how big your transformer is, how much you want to push air.
No, I mean
Natural. If it is natural, it will never achieve turbulent flow.
Okay.
It needs to go at least to 1.5 to 2 meters by second. That's where things start changing.
Model में capacitor use like
Mhm.
Transient.
Because right now solar doesn't depend
Transient
also
में
on
in a
the
में
length
steady
of
state
the
If you have a humongous pipe going up, probably.
Okay.
Okay.
That's true.
You cannot accelerate the wind enough without some trick or some sort.
In your model of a cable, capacitors were there, and you said that it's for the inertia.
Yes.
What like